Hey, what's going on, everybody? Welcome back to another video. In this video, we'll be talking about building our neural network model completely from scratch, along with getting it to train. So yeah, let's just get right into it. So for our model, we'll be using something known as a convolutional neural network, and this is a special type of neural network that is made for image data. So this is what we'll be using, and basically the way convolutional neural networks work is through two things, convolutions and maximum. So the way convolutions work is that they, in a sense, downsample our image. So what happens here is that given this 5x5 image, we have this 3x3 kernel that scans across the image and performs a dot product multiplication. And what happens is, uh, after it performs this multiplication of dot product, what happens is we're now left with a 3x3 grid of images. So from a 5x5 pixel image, now we're left with a 3x3 image. So this is a really effective way to downsample our image and be able to retain the same amount of information while being able to have a lower quality. And this can result in faster computations and whatnot. So with convolutions, as it downsamples and performs these operations, it also extracts key features and filters. And these filters will add another dimension. So you might have seen images that are like 32 by 32 by 256, and that the 256 comes from the amount of features that the model learns from. So for example, here, if we add this images of faces, what happens is the model might learn that this is like a high-end feature, right? We see that it has a general shape to the face, and this is more lower-end features. So as the model learns, it learns that maybe it might learn that there are two lines over here. It might learn that two semicircles. It might learn two circles and whatnot. And as it learns from that, it's able to predict whether, maybe in this case, if it's a human or an animal and whatnot. So this is the exact same thing we can apply. So using these convolutions and filters, we can help our model determine whether some sort of skin cancer is benign or malignant. The other thing that we use for convolutional neural networks is something known as Maxpooling. And what Maxpooling is that it takes in an input image and it takes the maximum value of a given kernel. So we can see here in this image that the kernel is 2 by 2, and what happens is that it takes the maximum value of it. So here in 4286, the maximum value is 8, and then in the next room, 2352, that is the maximum value here is 5. So it takes it like that. And we can also apply the same thing. So here, this is just an example, right? And, this can allow our model to be able to look the same in a sense, but be lower quality. So here we can see this line, and what happens is after this line goes through Maxpooling, we can still tell it's line, but it's shrink down and has a lot lower pixels. So we can apply the same logic to our neural network. So let's just get right into doing that. And yeah, just a quick refresher. I commented this code out, so if you'd like to follow along, I just commented the plt.subplot code from episode 1. So if you haven't watched that, then watch that first. And I also did add this mini code snippet. So I'm using a GPU, so I'm forcing my GPU to use some of my RAM memory for the GPU. And these other two lines basically import OS. And now what I'm doing right now is that I'm setting TensorFlow to only show me errors and warnings, especially because I have the CUDA drivers and whatnot. So it gives me a bunch of warnings and training. So, I want to keep this pretty clean. So we can do that. You can also, you won't have to do this yourself unless you have a GPU. So if you have a GPU, go ahead and put this. It'll help everything, like your terminal, look a lot more clean. So what we can do right now is let us import our model. So from TensorFlow.keras.models import sequential. So sequential basically means that we want to import a model that goes in like sequential order. So whenever we add our new layers, they go into sequential order. So we just need to specify that. So model is now equal to sequential. Okay, specified. Good. And we can also now start importing our layers. So from TensorFlow.keras.layers import dense, so just a regular neural network layer, dense conv2d, Maxpooling 2D. So we can import this. So, you know, the 2D for 2D images. And, you know, if you're not familiar with gens or whatnot, you know, a very famous YouTuber, Sentex, has a very good tutorial on the basics of neural networks. I'm going to be linking that in the description, so feel free to check that out. Anyway, so gens, con 2D, Maxpooling 2D, we can also do something with activation functions. So basically, with our neural network, we can use something known as activation functions. And basically, the way activation functions work is after our neural network outputs given value, we want to kind of like normalize or like threshold of value in a sense. And that's kind of what functions allow us to do. So in this case, we can use like the ReLU activation function. It works really well with convolutional neural networks. So we're going to be using that. Just in case you're kind of lost right now, the gist of neural networks is that we have an input vector x. So in this case, this will be like pixel values for our data set. So if we pass in like an image of a skin cancer, so x1 and x2 all the way to xm will be our input pixel values that are going to be put in a vector. And then what happens after that is each pixel value is multiplied by a weight. So that's going to denote it here with the sigma with wi(xi). So we take a weighted sum. So we multiply wi(xi) until wmxm, and we take the sum of that, and we add that with the bias. So in this case, the weight, the gist of the weights is that the higher the weight, the more important it is. So if I like the MNIST data set, for example, which is just a bunch of handwritten digits, it'll say that, for example, pixel values that aren't black are more important than the ones that are black. So that's just an example, and that's exactly what we can do. So then after you do that, we pass it to the activation function, and yeah. So let's just add activation function right now, or activation, let's just call it activation. Yeah. We also need to call flatten. So remember, our image is in 2D, it's a 2D matrix, but we need to make it a 1D vector, as we just talked about with the LSOB, so we can import flatten. Let's also import dropout. So dropout is another technique used in CNNs to prevent something known as overfitting. So what overfitting basically means is that our model memorizes on the training data and doesn't actually learn from it. So dropout resets the nodes, just like how we sometimes like might reset a laptop. So that's kind of the same thing here. So yeah, let's just start coding enough like chit chat. Model.add conv2d, 32, so our filter size. So remember, filter size over here, how many filters we want the model to learn from. So after that, 32, specify 3 by 3. So that's our kernel size. So over here, our kernel size. We also need to specify our input shape. So input underscore shape is equal to image size by 3. Forgot to note, but I changed the image size to 128 because 224 is unnecessarily too big, and we don't need something that big. So I'm just gonna leave it down to 128. You can even make it 64 and it'll work perfectly fine, but I'm just gonna leave it at 128 for now. So now I'm gonna add Maxpooling 2D 2 by 2. Oops, no. 2 by 2. And Maxpooling to take the maximum value of a convolution. And one thing I forgot was to add our activation function. So model.add activation ReLU. And basically we're going to be using ReLU right after convolutions because that just generally seems to work according to research and whatnot. So yeah, let's do that. And let's copy paste 3 times. There we go. And we can change this to be 64 over here for the second layer to extract more features. We can make this 128, but I'm going to leave it as 64 because, that seems to do the job for me. And yeah, we can also get rid of this right here, our input shape, because we already specified in the first layer, so this one need to repeat it. And now what we can do is now we can call on our dropout. So model.add dropout. I'm going to set it to 0.5 so it resets 50% of all the nodes. You can play around with this value. You can even put dropouts in these layers if you want as well. I'm just going to leave it as it is. I'm also going to call flatten now because now we want to flatten the image from a 2D matrix to a 1D array. And now we can call that out. Now we can call it on our first dense layer. So let's do that. So model.add gens of 512. So we can also call on our activation function, ReLU, and after that, we can now call on the final one, the final dense layer. So dense of 2, because remember, 2 classes, right? Benign and malignant. And we can also add an activation function for that. So this is known as the softmax activation function. Oops. No, wait. Softmax activation function. It's a special type of activation function that we can use that is specifically made for categorical classification. So in this case, we want to classify 2 things, which are benign and malignant. So softmax allows us to give probability values for this. So yes, we're done our neural network architecture. So good to hear if you've been following along. Now we need to compile the model, and we can do it. We have to call 3 different things. So like our optimizer, our loss function, and our metrics. So for our optimizer, I'm going to use TensorFlow.keras. Optimizer. I'm going to be importing Atom. So Atom's a very famous optimizer that is used in deep learning. So basically, it's a variation of gradient descent. And basically, what gradient descent is that it's a way to find the optimal weights for our model. So what happens is here W represents our weights, J of W is our loss function, and what happens is given a certain weight value, we want to see what our loss function is, and we want to decrease that weight all the way down until it finds a global minimum, which is basically the point in this parabola where our weight is the optimal value and the loss is at its minimum. So we can do that using Atom. So model.compile optimizer is equal to Atom, and I'm going to specify the learning rate to be 1e minus 3. So if you notice here that these arrows are kind of the step in direction of which the weights go in. So I'm going to leave that as 1e minus 3. So the weights change by 1e minus 3. So that's what I'm going to be doing. And we can specify our loss function. So remember, our loss function is the J of W over here to be something known as categorical cross entropy. And this is just a loss function for working with categorical cross entropy. Probably spelled that wrong, but that's okay. And that's a special loss function used for softmax, and it does the job. So it works. So yeah, and we got to specify metrics. Metrics is equal to accuracy. Basically means that we want to get the highest accuracy as possible. It's the only parameter we can specify. So yeah. And now that we've done this, I'd say we're now ready for model training. So model.fit. Yeah, fit. And now we want to call in a train data set. So we're going to pass in a train data set. If you're wondering about the X and Y's thing, I think I talked about that in the last episode. The train data set is a generator, so it has both X and Y's zipped up together. Remember, X is our data, and Y is based on the directory. So for every single directory in the benign class, it'll label maybe as 0 and malignant as 1. So yeah, that's just an example. So we can specify a train data set. 2, we can also call on a batch size. Remember, we need to specify that. So batch size equal to batch size. And we also need to specify something known as epochs. So epochs basically means how many iterations am I going to be learning from my data. So for example, if I were to do like the SAT, for example, I might do like the same test like maybe like 10 or 15 times before I actually do the actual SAT test. So in that case, it's a test data set. So we want our model to be able to, learn from its SAT tests to get better until it actually does the real one. So now that we specified epochs, we're now ready to go. So let's just call upon our beautiful CMD and pi main.pi. Okay, to here, it's working. Now it's calling on our epoch, 1 out of 10. And you see, now our model is officially training. So congratulations, you have now built a model that is currently training on detecting skin cancer better than you yourself, maybe. So, as you can see, model's learning right now. Its accuracy has now got up to 78%, and as it's learning, sometimes accuracy goes down, sometimes it goes up, and yeah, let's just wait for epochs. I specified it as 10. If you'd like to play around with different epochs, go ahead. You can play around with the epoch value being 20. You can play around with them being 5 or 1, but you'll see like pretty bad results. But yeah, and you can also play around with the optimizer atom. So why don't you change like from 1e minus 3 to like 1e minus 5 or like 1e minus 2? You can play around with this stuff and always do experiment because that's like the best way to learn, right? So yeah, and looks like our model is already halfway done through training. And yeah, so let's just give it a few more moments. So now it's 60% of the way. Now we're at its 7th epoch. And as you can see, we have reached accuracies of 81%, which is, very commendable. So now we're 90% of the way done. Let's just give the model a few moments for it to train and load. Look at that, we're already on our 10th epoch. So in just 10 more seconds, the model will be done training. So yeah, congratulations. You have now officially trained a neural network, a state-of-the-art convolutional neural network, to train and detect skin cancer. In the next episode, we'll be talking about visualizing our predictions and evaluating it on our test set, along with using a technique known as transfer learning. So until then, feel free to like and sub the video and turn on the notifications if you want to get notified for the next video. And yeah, until then, goodbye.